analgesics. I want us to start on narcotic analgesics. I'd asked Frida, I'd sent a small question, just something small that you, as we normally do, because we have done that with you, you draw the structures of the narcotic analgesics. You draw the structures of the narcotic analgesics. Just a minute, I plug in my charger of my phone. I'd request Frida that you draw the structures of the narcotic analgesics. I hope you've done that. If you haven't done that, please make sure you draw those structures. And not only will you draw them, look at them and understand them as we go along together to discuss them and make, as I try to make it much, much simpler for us. So I think it will be easier. How was that? Happen to the button of making it bigger. Oh, wow, there was that other button. I can't see it. Oh, they've changed it here. Wow. So we will start with the introduction, and I believe all of us have an idea of what narcotic analgesics are. I believe all of us also have an idea of the opioids, opium. Most of us have heard of the drug morphine, codeine. Codeine is a drug we use quite often. It used to be in the cough syrups. I don't know. I think now it has been withdrawn because of misuse and abuse. And therefore, when we talk about narcotic analgesics, I don't think it's something very strange to us. When we talk about the word analgesics, again, the word analgesic is not new because we have studied non-steroidal anti-inflammatories. Non-steroidal anti-inflammatories, drugs that relieve pain but work peripherally. Narcotic analgesics, again, drugs that relieve pain but work centrally. And because of the fact that they work centrally, they work in the mind. They can affect many other receptors. And that is why you find that the narcotic analgesics will have serious side effects like tolerance, dependence, and addiction because their receptors are in the brain. The non-steroidal anti-inflammatories, their receptors are in the periphery. Of course, some of those drugs will penetrate the BBB, as we have always studied, because of the fact that they have good lipophilic, they have got good high enough lipid solubility, so they'll penetrate the BBB, get into the brain, and sometimes, of course, they can give you some side effects that are originating from the brain. But for the narcotic analgesics, they must penetrate the BBB. They must get into the brain and bind the receptors to bring you the activity that they have because they are centrally acting. So the opioid analgesics reduce the perception of pain without loss of consciousness. So that, of course, is straightforward. The natural opioids are derived from opium. You've heard of people growing opium, which is the partially dried latex harvested from the opium poppy, Papaver somniferum. You are doing pharmacognosy, so I believe you have heard that. So we are talking about, you have this partially dried latex. It comes from this plant, the opium poppy, and it is known as Papaver somniferum. Opium contain morphine, it will contain codeine, it will have noscapine, papaverine, and the bain. So we are going to look at the classification of these opioids, but our main interest is morphine. And once we look at morphine, we will see that morphine can be structurally modified to give us codeine. These are the three. We are not looking at them for now. So we are looking at morphine and its derivatives. And when you look at morphine and derivatives, codeine is one of the derivatives of morphine. But we are saying morphine and codeine are naturally occurring opioids which are found in the opium or within the poppy of Papaver somniferum. The bain is a conversant drug that produces no analgesia, and as such, it is not used thinker. So that one was just a by the way, because we're not going to look at those. We're not going to look at the other drugs. But the importance of the bain is that it's an important synthetic intermediate in the production of semi-synthetic opioids. Because of its natural source, morphine and morphine derivatives are referred to as opiates. I hope it's taking. Wow. Yeah. So because of its natural source, morphine and morphine derivatives are all referred to as opiates. So as I have said, the main narcotic analgesics we'll be looking at is mainly morphine and all its derivatives, because indeed the narcotic analgesics, of course, there will be miscellaneous, but they'll still have some connection with morphine. So indeed, we will start with morphine and then look at all the other compounds. The classification. When you look at the classification, you can classify narcotic analgesics in different ways. You can look at their source, you can look at the receptor they bind. So we'll be looking here, you can look at also their origin in terms of the structure of the original compound. So we are first looking at the classification based on the receptor interaction and source. I've actually put them together. So you have what we call the pure agonist. And of course, by saying pure agonist, we're saying they are interacting with a certain receptor, it's the mu receptor, and they are pure agonists. They do not bring about any antagonist activity. So they are pure agonists. And then when you look at the pure agonists, you can further subdivide them. There are those which will be natural, there are those ones which will be semi-synthetic, and there are those ones which will be synthetic. So when we look at the natural ones, of course, is what we are calling the opium alkaloids. And the opium alkaloids are what we have said includes morphine and codeine. Then we have the semi-synthetic analogs. Again, when we look at the SAR, we'll be able to understand all these compounds. But you can see hydromorphone. This is a derivative of morphine. Oxymorphone, again, a derivative of morphine. Oxycodone, a derivative of codeine. And by the end of the semester, by the end of the lesson, we'll be able to understand what's the difference between morphine, morphone, and so on. But when you see this own, it tells you something. It tells you that that drug has a ketone, that one functional group within that molecule has been changed to be a ketone. So for this, when you talk about when you talk about morphine, it is where, when you look at the structure of morphine, you see a hydroxyl group in morphine being converted to a ketone, and therefore the name on. When we look at oxy, we'll be able to qualify all this. When we look at hydro, we'll see, why do we call it hydro? Why do we call it oxy? We'll be able to qualify all that. I hope I'm not going to lose some of this. Let's see. There is something that I've lost. I'm not tested, so. Yes, I think I have to keep changing. So now, we have looked at the natural, semi-synthetic, where we have said hydromorphone, and I've said don't worry, but at least understand hydro means there is saturation. You have added 2 hydrogen. Morphone, as I have said, on means there is an addition, there is a substitution of a functional group, and I have said this is a hydroxyl group substituted with an oxo group, which is a ketone. Then we have the synthetic compounds. These are totally synthesized. When you talk about semi-synthetic, means you are starting with morphine and then you derivatize it to the other compounds. Of course, when you talk about semi-synthetic or synthetic compounds, totally synthesized. And we have meperidine, levofanol, we have methadone, sufentanil. These ones are used as anesthetic drugs. Sufentanil, alfentanil, fentanyl, mefentanil, and levomethadine. We will be able to come across quite a number of them. Meperidine is the same as pethidine. So again, a very good drug, especially in the labor ward. So we will be able to come across them. We are just classifying them. And as I have said, one, I'm looking at the receptor they're interacting with, and then I'm also looking at whether that drug is naturally occurring, is it semi-synthetic, is it synthetic. Then we come to the second category. The first category was pure agonist. The second category is where we have mixed agonist, antagonist drugs. So it means they have both activities. They have both activities. They are mixed agonist and antagonist drugs. And again, we have the semi-synthetic, where you have nalbuphine, nalofine. Again, you can see these ones are derivatives of morphine. These ones are derivative of morphine. You're going to see synthetic. We have the pentazosine, which is a benzazosine derivative. Again, we're going to look at the structure, completely synthetic. But the original molecule was morphine. And then because when you look at the structure of morphine, the structure of morphine is huge. You remove some parts. You remove, let's say, the epoxide, which is down there. You remove a certain ring. You remove some portions of the morphine, and you make it slimmer. And when you make it slimmer, you still get derivatives or analogs of morphine, and pentazosine is one of them. But as I have said again, you'll be able to look at all this. These have agonist activity at some receptors and antagonist activity at other receptors. We're going to look at the morphine receptors. I believe, I don't know whether you have done the pharmacology of narcotic analgesics. Of course, you have the mu, you have the kappa, and you have the delta. So you have those three receptors. So a drug can bind the mu receptor and have agonist activity, and then bind the kappa receptor, have antagonist activity, and therefore the resultant activity, the ultimate activity, is what you're calling the mixed agonist antagonist activity of that drug. Then you have what we call partial agonists. I believe you in your pharmacology, I hope you have looked at the different receptors. What for my first, just a simple, so that I see whether we are still together. I'm also trying to learn how this thing is working. Today it is having different. Now, how do I go back to the original? Never tried it. Trying to go back. I'm just trying an error. So I wanted to ask you the first question. So my computer, I think the software is a little bit, something has changed. I think they've improved on the Kenneth platform. So it is showing some different things. So I want to ask the first question. What is a partial agonist? What is a partial agonist? I can see Olwanda offline. Teach offline. What has happened? Olwanda offline. What is a partial agonist? Olwanda is present but offline. Olwanda. I will keep noting. This is at 9:35 offline. And then we also have Teach 9:35 offline. 9:23. I'm waiting for you to tell me what is a partial agonist. Oops, Jesus. What is a partial agonist? What is a partial agonist? I believe we have done this earlier. I need many of you to be typing. What is a partial agonist? What is a partial agonist? You could answer quickly so that we move on. Don't take too long. Partial agonist? And no wonder it was showing you offline. You're back, eh? So they bind to an activate receptor but has a partial. Now you can't use the word you are trying to define, you cannot use it to explain. So you cannot say they have a passive activity. Now there, you need to use other words. A Frida Karopi passive agonist is that which it binds to and activates a receptor, but not to a maximum response as a full agonist. Very good, Karopi. Very good answer. Then we have, sorry. And we have Mugendi James, an agonist that does not induce maximum receptor activation. Okay, good. Evans, an agonist unable to induce maximum activity of the receptor. Very good answers. Drug that binds the receptor but are not able to bring about maximum response. Good answers. Joseph, it is a ligand, wonderful, binds to a receptor activating it but does not cause complete receptor activation. Very good, Joseph. Simon, even using the word ligand. Passive agonist, an agonist which is unable to induce maximum activation. Quite good. And from Shalina, a passive agonist, an agonist which is unable to induce. So at least I can see drugs that bind to an activator given receptor but have no maximum agonistic activity. Very good. So when we talk about a passive agonist, we are actually comparing it to an agonist. An agonist is the one to give you maximum activity. But now when you come to the passive agonist, it will excite, it will trigger pharmacological activity, but not to the maximum, as you have really correctly put it. So I'm happy about those answers. So we can continue. Iko na mingi kitu yangu. So we have now, we had gone to the mixed agonist, passive agonist, and we are saying we have the semi-synthetic, that they are indeed semi-synthetic. We have butorphanol. Again, you see this butorphanol is a derivative of morphine, and buprenorphine also a derivative of morphine. But this is not the best. Keep changing. I keep touching different. We learn. Yes. So narcotic agonist. Then finally, of course, you have the narcotic antagonists. And we know an antagonist is a drug that binds the receptor but does not activate the receptor. So that is very different from agonists, the passive agonists, which must activate the receptor. When we talk about an antagonist, they are what we used to call a dog in the manger. It sits in the manger, does not eat what is in the manger, but will sit there, and therefore, because you know dogs are feared, it will prevent the other animals from eating the food. That's the same thing we talk about an antagonist. An antagonist sits at the receptor. It has structural similarity with the agonist. So it will go for the receptor for the agonist, sit there, block it so that the agonist cannot sit on it. But it does not have the ability to trigger. So let us understand that antagonists do not trigger anything. They just sit, block, and prevent the access of the agonist. So do not have agonist activity at any of the opioid receptor sites. They block the opioid receptor, inhibit pharmacological activity of the agonist, and they, of course, they will precipitate dependent withdrawal symptoms in dependent patients. So those are the different types. That is a classification of of morphine and derivatives of the narcotic analgesics according to their receptor and their source. We can also classify based on the chemical structure. Then now only the opium now, alkaloids are classified into two types. That is just depending on their structures. We can have the phenanthrene derivatives. And here we'll have morphine, codeine, and thebaine. And when we talk about morphine, it will be morphine and its derivatives. But of course, there are derivatives of morphine that will not fit the phenanthrene structure. So we have morphine, we have codeine, and some of the derivatives. Then we have the benzoisoquinolone derivatives, which are the papaverine, noscapine, and narcine. As I have said, we only look at the first one, phenanthrene derivatives, which is mainly morphine and its derivatives. And we are looking at the opium, and of course, we have said it's a dark brown, resinous material obtained from poppy, Pavera somnifera capsules. And all we are saying is that when you look at the opium, it will give you two types or two structural two different compounds or two different derivatives with different structures. You have the phenanthrene and the phenanthrene ring. The phenanthrene structure is these three rings, and that's A, B, C. The A, B, C structure is what you're calling the phenanthrene ring, and you can have morphine and codeine. And then you have the benzyl isoquinoline, and you can see that's a benzyl, that's a phenyl ring, and this is the methyl group. So the whole of that now here, there is a benzyl, because the benzyl group is a phenyl ring or benzene ring joined to a CH2. And then, of course, this is what we're calling the isoquinoline, because the quinoline will have the nitrogen at position number 2. Now this has 1, 2, 3, has a nitrogen at position number 3. So if it were talking about the quinoline, it will have its nitrogen there, and that's isoquinoline. For now, we are not looking at these ones. Our interest is the phenanthrene derivatives, which are also the morphine derivatives. The morphine rule. I think first, I want us to look at the structure of morphine before we are able to understand the morphine rule. I had asked you to draw the structure of morphine, and I hope all of us have drawn the structure of morphine. When we look at the structure of morphine, we are saying there is A, this is the B, and that is the C. So that A, B, all of this, that's a A, which is an aromatic ring. That is B, which is a cyclohexene ring, and this is C, which is also a cyclohexene ring. So the ABC is what we are calling the phenanthrene ring, the phenanthrene structure. And then added to that, at this position number 4, 5, you can see we have this, we have an epoxide. So we have this, which we can say, because we can have a double bond here, we can call this a dihydrofuran ring, because of the furan ring will be completely without double bonds. So now when we look at this, we are saying A, B, C, the phenanthrene structure, and then D, or dihydrofuran ring, and then E is up here, and it is indeed a piperidine ring. If you have to draw this structure out, you can see it as 1, 2, 3, 4, 5, 6. So it has 6. It is actually a cyclohexane ring. It has 6 bonds, 6. So it's a cyclohexane ring, but of course it has a nitrogen. So when you have a 6-membered ring, whereby one of the members is a nitrogen, that is a piperidine ring. So indeed, this is a piperidine ring, and you can see at that position, of course, you have the methyl. So we are therefore saying, when we look at, and everybody should be able to draw this structure of morphine within a second. You should be able to draw it within a second. So when we look at the morphine ring, we are saying 1, phenanthrene ring, then D, the hydrofuran ring, and E, the piperidine ring. But as we look, as we are going to look at the SAR, structure activity relationship, we will realize that some of these are packages. You can drop them. You can drop some of these rings and create new molecules that have still very good pharmacological activity. But this is the original morphine structure. So we are saying the rings are A is aromatic, B is cyclo. Even B is still cyclohexene. I don't know why we are putting cyclohexene there, because there is this double bond there. So it has there, so cyclohexene there. C, cyclohexene also, it has that double bond there. And D, piperidine, and then the dihydrofuran ring. So that, of course, is very important. But when we look at the morphine ring, let us also look at its periphery. We have, this is the position we call number 1. I've put this structure this because this is how I learned to draw this structure many, many years ago, now more than 30 years ago. And I am never able to draw it otherwise. So that's why I've twisted it so that it agrees with how I know how to draw it from when I was taught by my lecturers many years ago. So this is position number 1. So when we start numbering, we are numbering from the aromatic ring. Number 1, number 2. So you can see very good substituent, very important substituent at position number 3, a hydroxyl substituent there. And when we look at, of course, this ring here, it is an aromatic ring. So we can say this hydroxyl group is a phenolic hydroxyl group. That is a phenolic hydroxyl group because it is attached to an aromatic ring. And then number 4, we jump that area. Number 5, number 6, number 7, number 8. And then from number 8, now we go to ring B. And this is number 9, number 10, number 11, number 12. Then we go to where the piperidine ring branches from, and that is number 13. And kindly, if you look at this number 13, I hope you can note something. It has that substituent, that substituent, that substituent, that substituent. So if you look at this carbon here, it is substituted. Its substituent is that's a carbon, that substituent is a carbon, that is a carbon, and that is a carbon. So we can actually correctly call this for this carbon a quaternary carbon. This is a quaternary carbon. A quaternary carbon is a carbon that has 4 carbon substituted, as 4 carbon substituents. And if you look at that, as I have said, that is a carbon there. This is a carbon. This is a carbon. That is a carbon. So that's a quaternary carbon. And indeed, that is one of the points where the piperidine ring branches from. So that is number 13. And then we go to this position as a number 14, and so that is our number, and this is our number 14, and then from there this should be our number 15, our number 16, and our number 17. So 14, and then this will be our 15. This here, there is a carbon here, will be our 16, and that is our number 17. So that is how, because remember, this is number 9. So we already have numbered that. So 14, 15, 16, 17. So our nitrogen, our piperidine nitrogen is at position number 17. Again, a very, very important group within the morphine and derivative. So we are saying all of the derivatives of morphine which possess this basic ring structure have a high addiction liability, which is proportional to the analgesic activity. So any of the morphine derivatives with this kind of structure, we do know that morphine is really abused. Why? It will cause euphoria, hallucinations, and so on. And of course, unfortunately, it will cause tolerance, it will cause dependence, and it will cause addiction. And indeed, in the world, we do have very many people who are suffering from morphine addiction and so on. Of course, morphine, as we're going to see, derivatized into other drugs like heroin and what have you, which are even stronger in terms of the activity compared to morphine. So that is one of the danger of the morphine and its derivative. Let us look at some of the structural requirements. And as we have looked at the structure, I have also mentioned them. The following structural features are important for morphine pharmacological profile. A rigid pentacycline structure consisting of, we are looking at morphine, mark you, not the other drugs. This is for morphine. So we are saying for morphine, it has a rigid pentacyclic structure. And indeed, that's what we have looked at. Rigid pentacyclic structure. It is it's a cyclic ring. This is a macrocyclic ring. Pentacycline 1, it's 1, it's 2, it's 3, it's 4, it's 5. So pentacycline, rigid, doesn't move, cyclic ring structure. And it consists of, which we have seen, A, benzene ring. Then B and C, 2 partially unsaturated cyclohexane rings, partially unsaturated cyclohexane rings, B and C, piperidine ring D. I've corrected this, must be a dihydro. If it's tetrahydro,